In the maritime domain, the ocean is highly conductive to acoustic energy. If you can be heard, you can be targeted. For a submarine, survival relies on an absolute, unforgiving rule: staying deeply submerged and completely silent. We're exploring the physics and engineering behind India's undersea modernization. Everything we discuss is based on declassified technical papers and open-source intelligence. If you appreciate deep-dive engineering breakdowns like this, take a second to like and subscribe. Let's look at the physics. Since the invention of the internal combustion engine, conventional diesel-electric submarines have operated under a severe tactical limitation. To run their silent electric motors while deeply submerged, they rely on battery banks with a finite energy density. Once depleted, the submarine is forced to ascend to periscope depth and raise a snorkel mast to ingest the atmospheric oxygen needed to run its diesel generators. This vulnerable phase is known as the indiscretion rate. It's the percentage of time a submarine has to expose its snorkel and thermal exhaust plume to the surface. During this time, the boat is highly susceptible to detection by modern airborne maritime patrol aircraft, which use high-resolution radar to spot a tiny mast, even amidst complex ocean clutter. For India, this engineering limitation is a pressing strategic vulnerability. The Chinese Navy is rapidly deploying Type 039A Yuan-Pras submarines into the Indian Ocean, and the Pakistan Navy is acquiring 8 Chinese-built Hangor-class boats alongside its existing fleet. Air-independent propulsion, or AIP, provides a technical solution to this surface reliance. AIP systems function as auxiliary power plants that generate electricity while the submarine is deeply submerged, severing the vessel's immediate need for atmospheric oxygen. In the contested choke points of the Indian Ocean, a conventional submarine without AIP cannot maintain a prolonged blockade. If it has to snorkel, it invites detection. Without stealth, a navy loses sea control. Globally, AIP technology is divided into 2 main architectural categories. The first category consists of heat engines, specifically Stirling cycle engines and closed-cycle steam turbines, like the French MESMA system. Both operate by combusting a fuel source, like specialized diesel or ethanol, with pure liquid oxygen. But heat engines possess tactical flaws. They rely on moving pistons, crankshafts, and rotating turbines, which generate vibrational noise that can couple with the pressure hull. Additionally, the combustion process produces carbon dioxide exhaust. Pumping this gas overboard against deep-sea hydrostatic pressure becomes increasingly loud and energetically parasitic as the submarine dives deeper. The alternative is electrochemical conversion, the fuel cell. Fuel cells bypass combustion entirely, converting chemical energy directly into direct current electricity, heat, and water. Because the core module contains absolutely no moving mechanical components within its structure, the vibrational acoustic signature is effectively zero. While fuel cells offer higher thermodynamic efficiency, their primary tactical value lies in achieving acoustic invisibility. Supported by solid-state power generation, these submarines can operate at ambient noise levels quieter than the ocean background itself. Western fuel cell designs, like the German PAFC, demand ultra-pure hydrogen. Because they cannot tolerate impurities, these submarines must carry massive, highly engineered hydrogen cylinders outside the pressure hull. This creates a significant weight penalty and complicates harbor refueling infrastructure. India's Defense Research and Development Organization, or DRDO, developed a different architecture, the phosphoric acid fuel cell, or PAFC. The PAFC operates at an elevated thermal baseline of 150 to 200 degrees Celsius. This temperature range makes the platinum catalyst far more tolerant to carbon monoxide and other fuel impurities. Because the system can handle less than perfect hydrogen, it allows for the use of an onboard chemical reformer. India's chemical workaround is the complete elimination of stored hydrogen gas. Instead, the submarine carries sodium borohydride, a stable chemical powder with exceptionally high energy density. Carrying a solid powder inside the hull is significantly safer and more efficient than storing volatile gas. During submerged operations, the powder is dissolved and mixed with water over a specialized cobalt-based catalyst. This hydrolysis reaction synthesizes pure hydrogen strictly on demand, feeding it directly into the fuel cell stacks to generate electricity for propulsion and internal loads. This reaction also creates a stable byproduct called sodium metaborate. Rather than being expelled into the ocean, which would require noisy pumps and leave a detectable chemical wake, This slurry is retained entirely on board in spent fuel tanks. Because the mass stays inside the hull, the submarine maintains its neutral buoyancy and trim without acoustic penalties. This engineering approach simultaneously removes the risk of explosive fuel storage, erases the acoustic signature of exhaust pumps, and solves the hydrodynamic problem of buoyancy management. Integrating this technology into an existing combat submarine requires a radical structural modification. You cannot simply drop an AIP module into the hull. This process, called jumboization, requires placing the submarine in dry dock and slicing the steel pressure hull in half. A new 300-ton cylindrical section, the AIP plug, is then meticulously welded into the center. This section houses the oxygen tanks, the chemical reactor, and the fuel cell stacks, requiring the rerouting of thousands of hydraulic and electrical lines. Marinizing experimental technology to withstand the shock and roll of open ocean combat is a long-term engineering challenge. To avoid keeping frontline vessels out of service during developmental testing, the Indian Navy shifted the first domestic integration to the INS Kanderi, with sea trials projected for 2027. To bridge the immediate capability gap, India is partnering with Germany's ThyssenKrupp Marine Systems for Project 75I. This $12 billion program will build 6 massive next-generation submarines equipped with sea-proven PEM fuel cells and high-capacity lithium-ion batteries. Project 75I acts as a strategic insurance policy. By mandating sea-proven German technology for the immediate fleet, the Navy secures the borders while the indigenous DRDO systems mature aboard the Calvary-class testbeds. These parallel tracks converge on Project 76. This program envisions a massive, fully indigenous attack submarine designed from the keel up specifically to house a scaled-up version of the DRDO fuel cell technology. With a 4,000-ton displacement, Project 76 will feature indigenous combat systems and long-range weapons. It will combine the domestic fuel cell with high-capacity battery modules for extended, silent lethality, far beyond the coastal littorals. These platforms will be capable of lingering silently at regional choke points for up to 3 weeks without ever surfacing to snorkel. In the acoustically complex environment of the Indian Ocean, this allows for persistent intelligence gathering and the ability to launch sudden ambushes. Mastering AIP technology transitions the Indian Navy from localized sea denial to persistent sea control, providing the advantage of absolute, prolonged silence in the dark waters of the Indian Ocean.